Hello, everybody. This is Paul Speciale. I'm the Chief Marketing Officer of Scality, and as usual, I'm joined on our podcast by Giorgio, our CTO and co-founder. How are you, Giorgio?
I'm great. How are you doing, Paul?
I'm doing great. I'm very excited because today we have something really tangible, right? Which is a kind of relevant news on storage performance in the world of AI and storage for GPUs, which is very critical. We've done a lot of kind of real-world testing in a lab. This is for a large client, and I think we want to share some of the different results. So this starts kind of a series of different benchmark testing that we've done.
Yep.
Maybe we want to demonstrate here that the net is we can always achieve the network line rates. It's ultimately the network that sets the limit. Our software is not the bottleneck. It gets out of the way. Is that a good way to speak?
This was the entire idea for this campaign is can we saturate the network? And now we know that we're going to need a faster network.
Okay, very good. And obviously networks are getting faster. Let's talk about that first so people have kind of a context of what the lab environment looked like and what the setup is so that they understand what we could theoretically achieve.
Yep. So we typically run on 6 servers to get started, but we had issues in this lab where one of a network card was at Connect X6 as opposed to 6DX, and they couldn't communicate properly on the network. So we had to remove one storage server from the equation. We still left up with 5, and even in this degraded mode, we got all the very impressive performance numbers we're going to show today. So the lab is RDMA enabled, and that's where we get a lot of a performance boost. You will see in the coming slides. The GPUs are RTX 6000 Pro, so Blackwell, very good GPUs. They don't have NVLink between them.
Yeah, I noticed that.
So we couldn't do things like loading a large model that's bigger than one of the GPU memory. So It was always local model that stays on one card. We've been able to generate a ton of sessions, more than 1,000 concurrent sessions on a single on the cluster, and really stress the system. And the networking is 400 gigabit ports. And we will show how we were able to saturate them.
Okay, very good. I looked at the switch. It's an old Mellanox, not old, but it's from Mellanox technology, so it's obviously a fast RDMA switch. I think the other thing to point out is that there is some local NVMe storage that we're going to use as kind of a baseline, right?
Yeah, local on the GPU servers.
Yeah, okay, very good. All right, so I think that sets the context on the hardware side. So why don't we take a look at the software? The software stack here really had 4 components.
So I think we showed numbers previously using the NIXL library from NVIDIA, and it was all storage to storage kind of thing, or GPU to storage, but only looking at the bandwidth transfer. In this test, we're looking at the end-to-end from vLLM that has a model that actually processing tokens. We use ModelExpress from NVIDIA for loading the models into vLLM. We use NIXL for all the data transfers, and the NIXL plugin from Scality that gives you both ADI, S3 API, and the native AI API over RDMA.
Very good. All right, so that sets the software stack. Let's talk a little bit about the different test paths that we wanted to look at. There's variations here, right? Because there's S3 on the normal TCP transport, but also on RDMA. And then we have the combination of the same on our native API.
So the baseline would be local NVMe storage. This is TLC. The same flash drives are being used on the storage nodes and the GPU. We're benchmarking 2 different object protocol. The S3 API as an object store, we fully support S3, and we can do it on TCP and accelerated via RDMA. And also we are comparing with our native API, where you can go directly talking to the low-level API in our nodes. Okay. And all of that is done through the NIXL plugin.
I should say that my expectations obviously are that local NVMe is already super fast and that it should win, but maybe that's why it's an interesting baseline for comparison, huh? So with that, let's talk a little bit about the various things we wanted to test. There were 6 test phases. Obviously, you have to set the stage with how much raw bandwidth there is, right?
Yeah.
So you know what.
And so we wanted to do a podcast for each of the different tests, and so we benchmarked the system. Everything was working as expected. Then the interesting pieces that actually stress the vLLM and the GPUs were model loading, time to first token. So the model is already loaded, but the KV cache is offloaded somewhere. And we want to see the time it takes to receive the first token output from the model. And then inter-token latency is as you are generating the response, LLM do that one token at a time. People don't always know that. And we want to see what's the latency in between token output. So that's another thing we measured. Then we measured pushing the entire KV cache on storage and having a lot of sessions. I think we were up to 1,000 sessions. What's the impact on performance? And then checkpointing, which is going to be training and having to very quickly dump all the weights into storage.
Okay, very good. At the top, it also says that we had 4 models, so varying number of parameters in the model too.
Yeah, the biggest one was Gamma 27B. And I think right now the engineers are doing tests with a GLM, so we will have additional numbers.
Okay, so in the end, I think we want to make kind of the point that there's 2 APIs against 1 object store. Both are capable. You see the same object through both, and it gives flexibility to get the ultimate performance if you need with RDMA.
So I was talking to a customer this morning that has a need for using us with GPUs. And what they describe is most of the data is going to be written via S3, right? It's coming from external tools, maybe external companies. They're doing exchanges in terms of photos, videos for their training. And this is going to use the S3 API. Okay. So you see a different type of apps at the top, ingest, training, things like that, even agents, that need to fetch a document. And we don't expect everything to be ported to another API. So we're going to keep the S3 API. The good news on Scality ADI is it doesn't matter which API originated the data. You can always serve it via RDMA. So you could do S3 TCP and then serve it to the GPU via RDMA, S3. Or you can also serve it via our native APIs. Okay. So it doesn't matter that the data didn't come from a native API, it can still be accessed this way. And I think that's key into this benefiting from both the compatibility and the performance boost. And the other aspect is in training, that's where we see the most need for the fastest possible API for writing. And then you could train and write directly to the native AI API. In that case. And I think we will share these numbers in a upcoming podcast.
Okay. All right. Very good. So I guess the thing we should understand then is what are the differences between these 2 APIs and how does the native go a little faster or significantly faster?
Yeah. So the S3 API has to go through a lot of checks and metadata lookups. So the object is first in a bucket. So you need to fetch the metadata from the bucket, which is an operation that's going to take time. That's on top of actually getting the data. Then you have a lot of authentication checks that you have to do, and that's many extra communication per request. When you use the native API, you get away with the authentication first, and then you can actually get the data as fast as possible with much less overhead and less round trip, and no need to go look up in a metadata engine. Yeah. So that gives you a much faster performance.
Okay. So it really does show that there is overhead in the richness of the S3 API. We've talked about this before, right? It's one of the reasons that even Amazon did S3 Select, but it probably didn't go far enough, right? Because it's still not.
And I think you meant S3 Express.
S3 Express. I'm sorry. S3 Express. That's exactly right.
Yep.
Okay. Very good. So in the end, if we compare the 2 and look at, 1 link and 4 links, it looks like the native really does win. It gets nearest the line rate.
Yeah. So you see that on TCP, the S3 API couldn't saturate the network.
Right. I see that.
But we were able to saturate it using the native API. So that's the 2 left bars. And then you go into RDMA for the next 2 sets. And you see that RDMA allows you to use 100 gigabits per second in that particular test. This was 2 gigabyte object, 32 operations in parallel. So a rather large object. It will be different with a smaller object. You would see that even with RDMA, S3 couldn't saturate, but with 2 gigabyte object, it was possible. And then as you go to 4 times 100 gigabit, you see that S3 overhead is really visible.
Okay, I get it. And just from my mind, the ultimate bandwidth limit is the 4 100 gigabit links, which is 400 gigabits, and that's 50 gigabytes. So we're really
a little bit less than 50.
A little less than 50. So we're really close to the line rate.
Close to the limit.
Okay, very good. All right, so that is clear. So ultimately, how does this show out in terms of the model loading time?
Yep. So in that test, we are loading the model into the GPU from storage. And you see that the local NVMe took 18 seconds to load that model. That test is using only one of the drives locally, and that's the way that vLLM is configured. I think you could do a red and do some striping, but that's not a default configuration. So we try to keep things simple, but it gives you a good baseline to compare with. When you go through the S3 API, RDMA or TCP, you're getting faster response. And that's because the object store automatically shard data across multiple servers and nodes. So now you have a performance of multiple drives and nodes. And you get to 12 seconds, but you notice that it's the same performance for RDMA and TCP.
It's surprising, right?
So the reason why is because the model loading itself is very sequential.
I see.
So you're basically not using the object store to the fullest extent. So and we know how to optimize it, the model loading. There's actually a patch coming into the tool that we use that will parallelize better. And so you will see a higher performance with RDMA in that case, even with S3. Then you go to a native API, and clearly the faster the link, the faster the loading.
And I see that I almost get exactly the 4x speed up going from 1 link to 4. So
yes,
that's good.
And it doesn't get full LAN rate, not because of the transport itself, but because GPU loading actually requires the GPU to work. So there's some activity on the GPU, and it's not just one big fetch from storage.
Yeah, makes sense. Okay. It's a dramatic difference. And again, to reflect back that the expectation was that local drives would just be blazingly fast. I do understand that it was a kind of a straight out of the box baseline, but still the result stands, right? You're going from nearly 20 seconds to 2.
That number is pretty fast because it's still it's 55 gigabytes of data. Right?
Yeah, not nothing. Agreed. Okay, so out of that time, then, if you break it down, where does the time go? Where is it spent?
Yeah, so just to give an idea, the wire was around 36 gigabytes per second in the BF16 test. So we tested with different type of quantization, but this one is BF16. And so there's some time spent into setup on the software side. Call it plugin setup. There's time spent after loading on the GPU itself because he has to take the weight and actually store them in memory in a way that's useful for its tensor engines. So there's some work that's happening, especially when we use a quantized model. It requires additional work to get them ready for processing.
I get it. Okay, so
next
really,
slide, I think we have.
Go ahead.
I think the next slide has more details.
Yeah. But I mean, my takeaway here is that it's the wire transfer time that dominates, obviously, right? But there's obviously this overhead at the beginning and end.
In that particular example, the storage time was total time between plugin setup and wire transfer was 192 seconds, and the GPU added something like 0.40 second, and the setup was around the same.
Okay. All right, that makes sense. It's an interesting result. Then you mentioned that we were using FP16, but you tried it with various different quantizations.
Yeah, in GPT-Q4-bit FP8. So you see that the bigger model takes longer to transfer. That's the blue line, right? Makes sense. And then there's a various amount of time taken locally by the GPU to process the weights into something that's usable for inference.
Okay.
And that's the orange line.
Okay. Very interesting. Well, in the end, then we can conclude what we said at the beginning, right? That the software is not in the way. You can really go point to point.
Yeah. And our goal is to do tests on a faster network, so 2 times 400 gigabit per second. And we keep optimizing every element of the stack to be able to get line rate.
Okay, very good. It's a super interesting takeaway. I think we want to come back with another episode and talk about the KV cache performance that we ran in the same environment.
Yes.
So with that, thank you very much, Giorgio, and we'll see you on the next one.
Thank you, Paul. Thanks, everybody.